Beautiful mind here. This serves as our lecture for Calculus for Business. We're continuing chapter 3 on applications of differentiation. And today, we'll be looking at section 3.3, graph sketching, asymptotes, and rational functions. A few objectives. We like to find limits involving infinity. We like to determine the asymptotes of a function's graph. And we like to graph rational functions. A rational function is a function f that can be described by f of x equals p of x over q of x, where p of x and q of x are polynomials, with q of x not the zero polynomial. The domain of f consists of all inputs x for which q of x is not equal to 0, right? Because we can't divide by 0. So the line x equals a is a vertical asymptote if any of the limit statements are true. So the limit as x approaches a from the left of f of x equals infinity. Okay, so vertical asymptote. So as x approaches a coming from the left, the y goes to infinity. As x approaches a from the left, the y goes to negative infinity. As x approaches a from the right, the y goes to infinity. As x approaches a from the right, y goes to negative infinity, right? So as x approaches some number, if y goes to plus or minus infinity, as x approaches some number either from the left or the right, and if y goes to either plus or minus infinity, then plus or minus infinity, then that means we have a vertical asymptote. The graph of a rational function never crosses a vertical asymptote if the expression that defines the rational function f is simplified, meaning that it has no common factors other than -1 or 1, then if a is an input that makes the denominator 0, the line x equals a is a vertical asymptote. So long story short, like if a number produces a 0 in the denominator and not a 0 in the numerator, then that number is going to be a vertical asymptote. Okay. So determine the vertical asymptotes of the function given by, we have this this function as you see. So at first glance, the values of x that make the denominator 0 would be what? X equals 0, x equals 1, and x equals -1, right? But if we plug in x equals 0, that's going to give us 0 over 0, right? So this guy cannot be a vertical asymptote. This is going to be a hole or a gap in the graph when x is 0. X equals 1. If we plugged it in, that's going to give us -1 over 0. So that one's going to be a vertical asymptote. And when x is -1, that gives us 3 over 0. So x equals plus or minus 1 are going to be our vertical asymptotes. But when we simplify, the term that produces x equals 0 gets canceled out. So that one's not a vertical asymptote. Copy. Okay. So since 1 and -1 make the denominator 0, x equals 1 and x equals -1 are vertical asymptotes. For you. And then we have this definition. The line y equals b is a horizontal asymptote if either or both of the following limit statements are true. As x goes to negative infinity, y approaches some number. If as x goes to positive infinity, y approaches a number. So as x goes either to the far left or the far right, we see it's a horizontal asymptote if y approaches some number. Rational function may or may not cross a horizontal asymptote. Horizontal asymptotes occur when the degree of the numerator is less than the degree of the denominator. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. The degree of a polynomial in which one variable is the highest power of that variable. So we have a horizontal asymptote. Basically, when this was first introduced to me, there were 3 scenarios. The first one is when the degree of the numerator is less than the degree of the denominator. Then the horizontal asymptote is going to be y equals 0 or the x-axis. When the degree of the numerator is equal to the degree of the denominator, then we take the ratio of the leading coefficients. And then, that's what these two are saying, less than or equal to 0, less than or equal to the degree of the denominator. The third case was like if the degree of the numerator is larger than the degree of the denominator, there's some other cases that kind of pop up once the degree of the numerator is larger than the degree of the denominator. Right? So determine the horizontal asymptote of this function given by this. So notice that the degree of the numerator is equal to the degree of the denominator. So then this horizontal asymptote here is really just the ratio of the leading coefficients. So this horizontal asymptote would be y equals 3/2. So then for some context, what we can do to see where that comes from, let's start by factoring out the top and the bottom by x squared, right? We're basically kind of like multiplying by 1 over x squared on top and bottom. All right, we're multiplying by 1 in this form. So then if we do this, 3, the second one becomes 2 over x. The third term becomes minus 4 over x squared. Later, we have a 2 minus 1 over x squared, right? So then with this, if we consider the limit as x goes to positive infinity, let's do it like this. So we want to consider the limit as x goes to positive infinity, right, to the far right. So as x goes up to the far right, this term goes to 0, this term goes to 0. As that denominator gets bigger and bigger and bigger, and the numerator is a fixed number, these terms all essentially go to 0. The further and further to the right we go. So then that's where we're left with the 3/2. And now we can do something analogous as x goes to negative infinity. Determine the horizontal asymptote of the function given by this. First, divide the numerator and the denominator by x squared. We got this, so we did the same thing. Find the limit as the absolute value of x gets larger and larger and larger. So as x goes to negative infinity, you got 3/2. As x goes to positive infinity, you got 3/2, right? It's the same kind of argument. So thus the line, so we, and we probably should have considered the negative infinity in addition to the positive infinity. Okay, this is fine. Leave as exercises for you. And then we have this definition. We have that a linear asymptote that is neither vertical nor horizontal is called a slant or oblique asymptote. For any rational function of the form f of x equals p of x over q of x, a slant asymptote occurs when the degree of the numerator is exactly 1 more than the degree of the denominator. A graph can cross a slant asymptote, right? Okay. So find the slant asymptote. So whenever the degree of the numerator is larger than the degree of the denominator by 1 degree, as in this one, to find the slant, you basically just you can either do polynomial long division. In this case, we can do synthetic division. So I'm going to go ahead and do synthetic division. If I'm going to do synthetic division, the x value that makes 0 in the denominator goes in a chair. So we're going to put 1 in the chair. And then we write the coefficients of the numerator, right? And since we got to make sure that every power is accounted for. We started with the degree 2. We need to account for, we need a placeholder for that degree 1. So the coefficients are going to be 1, 0. Okay. Now when we're doing synthetic division, the first one just comes down. On the diagonal, we multiply. So 1 times 1 is 1. Vertically, we add. Diagonal, we multiply. And then we add. We started with the degree 2. So now at this stage is a degree 1. We were finished with x plus 1. And this guy is a remainder. Right? Finish your division, the equation of the slant asymptote is going to be y equals x plus 1. polynomial long division, right? And I think they still got their x plus 1. You see the remainder of -3. See that as the absolute value of x gets very large, that -3 over x minus 1 approaches 0. So for very large absolute value of x, the expression x plus 1 is the dominant part. So then as the absolute value of x gets very large, this guy goes to 0, right? And the left equals x plus 1 is going to be our slant asymptote. Of exponential and log functions. An exponential function of the form f of x equals a e to the bx, where b is positive, has a horizontal asymptote y equals 0. The x-axis as x tends to negative infinity. So if you think about an exponential function, the general shape of an exponential, it kind of starts off running along the top part of the x-axis. It passes through the point 0, 1, and then grows exponentially. So again, the general shape of an exponential function, it has a horizontal asymptote going off to the left, right? So that's why this has its x goes to negative infinity. When our b is negative, so when it has a negative exponent, that we multiply the inside by a negative, so that caused it to flip horizontally. So now we have exponential decay. So now it y equals 0, or the x-axis serves as a horizontal asymptote as x goes to positive infinity, right? The first one was as x goes to negative infinity, but now because we're dealing with exponential decay, y equals 0, or the x-axis is our horizontal asymptote as x goes off to the far right. You just got to think about the basic shape of exponential functions and then go from there. The log function, generally it starts off running along the right-hand side of the y-axis. It passes through the point 1, 0, and then kind of goes off to the right. So then log functions generally have a vertical asymptote. The form natural log of x minus a has a vertical asymptote at x equals a as x approaches a coming from the right, right? So for instance, if we think of just natural log of x, that's going to be the same as natural log of x minus 0. So then x equals 0 was our vertical asymptote for the general, right? If we just had natural log of x. And then so this one, the next one, they essentially multiplied the inside by a negative, right? So we in the third line, we had x minus a. And the fourth line, if you multiply the inside by a negative, you get this guy. And then, so multiplying the inside by a negative flips it horizontally over the y-axis. So now it basically is diving to negative infinity as x approaches a coming from the left, right? Has a vertical asymptote as x approaches a from the left. So that's kind of a mouthful. Let's work some examples and see, if it'll be more clear. Like describing it is one thing, but then working it out is a totally different experience. Find the horizontal asymptote of this. Now we're dealing with an exponential. Let's think about this. As x goes off to positive infinity, right? It's basically this term here. We have, if we focus on this term, this is what exponential decay. So as x goes up to the far right, this term goes towards 0, right? To infinity, this guy goes to 0. Okay, let's write that down. So as x goes to infinity off to the far right, the expression that 25e to the negative 0.04x, that tends to 0, right? Up to the far right, let me see, the limit as x tends to, here, let's clean that up. Infinity of f of x is to 200, because you're going to have 200 over 1 plus 0. Let's consider the limit as x tends to negative infinity of this function. So if x is going to negative infinity, that's what? Positive. So that makes the whole denominator blow up to infinity. So then a fixed number over a really large number is practically zero. So as we go off to the far left, the whole thing tends to zero. Okay. Right, it tends to 200. To the far left, it tends to zero. Let's see what the prepared notes say. So as x goes off to positive infinity, this term tends to zero. So the limit as x goes to infinity of f of x is the same as 200 over 1 plus 0. So we got that. Right? Equals 200 is a horizontal asymptote as x goes is one of the horizontal asymptotes. Now as x goes to negative infinity, again this term goes to positive infinity. So the limit as x goes to negative infinity of f of x is going to be 200 over 1 plus infinity. A fixed number over a really large number is zero. Zero is also a horizontal asymptote. So we just consider it going to the far right, going to the far left. And here's a graphical representation of this. Much faster than I anticipated. A strategy for sketching graphs. First, you might want to consider any intercepts. So identify your x and y intercepts, then any asymptotes. So vertical, horizontal, or slant or oblique. We want to find any derivatives. So first derivative and second derivative in the domain. Any critical values from the first derivative. Okay. Find the intervals over which the function is increasing or decreasing at any relative extrema. Any points of inflection. So that's where the second derivative is going to be either zero or undefined. The intervals of concavity, like, once you have your point of inflection, you can identify over what intervals the function is either concave up or concave down, and then put all this together. We're going to do a few of these. Let's see. I'm excited. Okay. We're going to need space too. So just going to have to bear with me. Let's give it a go. Okay. So here, we're asked to sketch the graph of this. Let me start by, instead of starting here, I'm going to go ahead and get a copy. F of x equals, now on the bottom we have x squared minus 4 under 8. I'm going to take this. One of the first things, the suggestion is identify your intercepts, any intercepts. Intercepts, I prefer to start with the y-intercept. Y-intercept, I've noticed is like easier than the x-intercept. To find the y-intercept, we set x to 0. If we set x to 0, if you can find the y-intercept, it's a good idea to just go ahead and find your x-intercept. Okay. To find the x-intercept, we set y equal to 0. But when is a rational function equal to 0? When the numerator is equal to 0. So notice that this numerator will never be 0, so there's no x-intercept. So we're going to say none. And I'm going to highlight our results like this. None. I don't know what that was right, but that's none. Okay. So then now, again, when we found the x-intercept, we set y equal to 0, but setting y equal to 0 in this context was the same as setting the numerator to 0. So if we can set the numerator to 0, we can also set the denominator to 0. So then that takes us to the next one. So the next suggestion, after the intercepts, let's find any asymptotes or asymptotes. Okay. So let's start by setting the denominator. We want to set the denominator equal to 0 and solve. So there are no holes or gaps or breaks, right? There's no x value that's going to make it 0 over 0. So then if we set the denominator equal to 0 and solve, add the 4 and you get plus or minus 2. Right? So these are going to be our vertical asymptotes. And again, what we did, we set the denominator equal to 0. Okay. So then naturally, here, let me put this a little bit. Okay. So then if we can find vertical asymptotes, let's go ahead and see if we have any horizontal. So then we need to do basically compare the degree of the numerator to the degree of the denominator. The degree of the numerator is less than the degree of the denominator. So our horizontal asymptote is going to be y equals 0. Okay, let me highlight my results. So since we have a horizontal asymptote, we should not have a oblique or slant. Okay, so then we can do look at the first derivative, second derivative, and the domain, right? So we'll say derivatives and domain are the third suggestion. So again, if our f here, for the sake of space, I just go ahead and hop into f prime. So I'm going to use the low D high minus high D low for low low. So the bottom, which is this guy, derivative at the top is the derivative of 8 is 0. So there's that. The bottom times the derivative of the top minus the top times the derivative of the bottom is going to be what? 2x over the bottom squared. So there's going to be x squared minus 4 squared, right? I think all of this collapses to 0. So then our f prime minus 4 squared under 18x, right? Prime, let's go ahead and find f double prime. Basically take derivative of that. So we're going to say the bottom, which is this, times the derivative of the top, which is going to be times the negative 16, minus the top. It's going to be 2x squared minus 4 times 2 over the bottom squared. X squared minus 4. I'm going to just shrink this down. Top minus the top times, so that is the multiplication. Simplify this any. It looks like both terms have that x squared minus 4, at least one of them. So let's highlight what we can factor out. They both have at least one of these. There's one there and one here. Looks like they both have that negative 16. So there's one here and one here. Let's factor that out and see if we can get some cancellations going. Out the x squared minus 4 times the negative 16. If we have one x squared minus 4 left here, that negative, wait a minute. Okay. X, I just had the 16. Times the root of the top. Yeah, minus the top times the root of the bottom. Yeah, okay. So that, but we could factor out the negative 16. Okay. So then what we're left with, we got 2x times 2x is 4x squared. So again, did not make mistakes. What's left was that minus 2x squared minus 4 has already been accounted for, okay? And then we still have this x squared minus 4 to the power of 4. So then, at that point, this can now cancel one of these, turn this into a 3. Most that we could do. This negative 16. X squared minus 4x is a negative 3x squared. Or back again. I don't see anything. I mean, you could factor out a negative from the top, and then you can pretty much write it like 16 times 3x squared plus 4 over x squared minus 4. Okay, to the power of 3. Okay. Oh, that's difference of squares. That's x, but that doesn't. I don't think anything cancels. So we're gonna let that be. So let me highlight the first derivative, and we'll just reference it as needed. Our second derivative, we got this. Okay, so hopefully we didn't make we kept our mistakes to a minimum. The domain of the original except plus or minus 2, right? Not equal to plus or minus 2. Those are going to create zeros in the denominator. We can't divide by 0. Okay. And now we can use the first derivative to talk about like increasing, decreasing, and extrema, like max and min. Let me see. Let me do another page. So then the fourth suggestion, go ahead and find any relative extrema. So using the first derivative. So 4, I'm going to say find relative extrema. With that first derivative. So for extrema, the relative extrema are going to occur, the critical values, the relative extrema, I should say. I mean, the idea is that we're finding the critical values, right? That occurs where the first derivative is either 0 or undefined, all right? So then we take the first derivative for our critical values. If we set, for this one, we're going to set the numerator to 0. So, oops, that we get is going to be x equals 0. That makes the derivative 0, right? Another critical value is going to be x that makes it undefined. Let's see. So when x is 2, that makes a 0 in the denominator. So 2 additional critical values are going to be x equals plus or minus 2. Right? So those are numbers that we want to consider. They're candidates for potential relative max and min, relative extrema, right? So we're going to take these critical values and put them on our number line. I'd be like so crooked. Here, let's do let's line it. It's fine. And let's plot these critical values. So we had 3 of them when x was 0 and then 2, right? And we want to look at these in the first derivative. So in f prime of x. -2 into the first derivative, I think we got a 0. I'm sorry, we got undefined. This is undefined. What we want to do, this is going to tell us whether the function is increasing, decreasing, or constant. So we want to test a number to the left of -2. Plug in -3. If we plug in -3, it's going to be what, 9? 9 minus 4 is positive, so the denominator is going to be positive. If we plug -3 in the numerator, that's going to make the numerator positive as well. So all the numbers to the left of -2 result. So our original function should be increasing. -2 and 0, let's test when x is -1. If we plug -1 into the first derivative, that makes the numerator positive. 1 is negative, squared is positive, so this is positive. So then everything here should be is positive, which means our original function should be increasing here as well. So that means that -2 is not a relative extreme. Based on this, as long as we're doing this right. Let's try when x is like 1. So if we plug 1 into the first derivative, the numerator is negative, positive. So that makes all of these values negative in the first derivative, which means our function should be decreasing. 0 and 2. And then to the right of 2, let's try 3. If we plug 3 into the original, we get a negative on top, and a positive on bottom. So that makes all of these negative. So we found one extrema. We found the relative max. A relative max when x equals 0. And then what we need to do to find the corresponding y, we plug this back into the original f of x. So 0, y is -2, right? -2. That was using the first derivative to find extrema. Go ahead and use the second derivative to identify any points of concavity. Right. So this was about the first derivative. The fifth suggestion is about let's explore the concavity and points of inflection. Concavity. second derivative. That we got. Hopefully, we didn't make any mistakes or we kept it to a minimum. Okay. So of concavity, those are going to occur when the second derivative is either 0 or undefined. So this can be 0 if we set the numerator to 0 and solve. Here, let's do that. We got this 16 times 3x squared plus 4. If we set it at 0, we divide both sides by 16, we get this. 4 divided by 3, we get x squared equals -4 by 3. So there's no x that's going to make that 0, right? Let's see if there's an x that makes the denominator 0. So I'm just going to like strike it. There, let me put in my headphones, switch it out. Denominator to 0, let me see. We got this x squared minus 4 cubed equals 0. You can take the cube root on both sides. You get x squared minus 4 equals 0. Add 4, so x equals plus or minus 2. So when x is plus or minus 2, those are candidates for points of inflection. All right. So then what we do is we take that and we need to basically do the interval test like we did with the first derivative. We take those results. So let me copy, paste. And we look at them on a number line. So here's our -2, here's our +2. So then we need to choose test intervals and evaluate them in the second derivative. So for instance, if I take that -3 and plug it into the second derivative, let's see, I think all of this is going to be positive. 9, so it's going to be positive. It's going to be positive over positive. So left of -2, the second derivative is positive. So that means our graph should be concave up. Between -2 and 2 is the simple number is 0 to test. So if I plug in 0, this is positive. If that's cubed, that's going to be negative, right? So if we plug in 0 into the second derivative, we get a negative result. So that means our graph should be concave down between -2 and 2. And then to the right of 2, we could test 3. If we plug in 3, this is positive. 9 minus 4 is 5. This is positive. So it goes back to concave up. So we got the right of 2, it was positive. So our graph is concave up. So then we have 2 points of inflections. So then our points, or in this case, our points of inflection, when x is -2 and +2, and then we just need to find the corresponding y's from the original. So in either case, okay. So it looks like, yeah, because I think for our domain, we said that, where is it? X cannot be plus or minus 2. So then there are no points of inflection. I'm going to leave the notes, right? We're going to say points of inflection, we got none. All right, this is fine, this can happen. So we got no points of inflection. And then usually what I do, after taking all of that, I usually like to choose a few additional points. I mean, honestly, this is enough. I don't think we need any additional points. let me see what the suggestion was before this one. Concavity, yeah, we did that. We found the where it was okay, so let's put all this together. All right, so we got 2 pages. It's a little intense and it takes practice, but it's possible, right? So now with this page, no, let's just go here, paper. Actually, this might be a little bit easier. Okay. So now let's put all this together. Let me see. Points of inflection. We got no points of inflection. X, Y is 2 there. Plus or minus 2. 2. Okay, let's go like 6. Let's go 6 in all directions. So we're going to create a graph. I'm just choosing a point. This will be my x-axis. Okay, here's our y-axis. So again, positive x is here, positive y is here. We said we want 6. Okay, that's fine. So we'll label it like this. Let me see. We can go 1, 2, 3, 4, 5, 6, 7. That's good. And then we're just going to take that. Let's do it like this. Right there. Okay. Okay, that's decent. And I'm gonna go ahead and get a copy of this page. Let me just copy and paste, and I'll bookmark it as a reference page because I know I'm gonna need that again, a blank graph like that. Okay. So then let's label this. So this was our origin. We counted this as 1, 2, 3, 4, 5, 6, 7. I don't know if that's any easier. We can try it. Copy and paste. 1, 2, 3. Okay. These are negative. Okay. I guess this wasn't too bad to drag. Okay, and these guys are negative. And I'm actually going to get a copy of this one. Let me delete this one. Okay. All right, and I don't want to mark up this one. Okay. All right. So now let's put all this information together that we got. So if we go back to the first one, we got a y-intercept of 0, -2, and no x-intercept. So then I'll do it like this. 0, -2 is here. Okay. Then let's see. So then asymptotes, we got vertical asymptotes. We got ±2. Okay, so let's go ahead and add that. So what I'm going to do for that part, let's copy, paste, actually, style, can we change it from? Okay, that's okay. So from here to here, style of this thing, and we need dash. Okay. And I'm just going to copy this and paste. So these are the vertical asymptotes. Okay. So we got our vertical asymptotes. We had a horizontal asymptote of y = 0. So let's go ahead and capture that. That's just going to be this guy. Okay. And that's y = 0. We've already used the first derivative, second derivative, the domain, everything except -2. So we said we had a relative max. So that should be a amount that, relative max. And then it should be concave up, concave down, concave up. Okay. So then I would choose an additional point, right? So yeah, just usually what I do is a few additional points between and beyond I usually do the x-intercepts and any x-intercept or any vertical asymptote, right? So for instance, when x is -3, I want to find the corresponding y from the original. So if we plug in -3 in the original, 9 - 4 is 5. So we get 8 by 5. So that's what? 1 3/5. So when x is -3, so we got something like this, a little bit past halfway. So it's about here. We probably could have did symmetry. This was -3, comma, I think we got 8 by 5. And I think if we do +3, we get a similar result. So here's here, 3, comma, 8 by 5. We could have did the test for symmetry like in college algebra. And I really think that this is enough, right? So then what's going to happen, we get a graph like the following. All it is, we start close to this asymptote, we pass through this point, we finish close to this asymptote. We start close to the asymptote, we pass through this point, we finish close to the asymptote. We start close to the asymptote, we pass through this point, we finish close to the asymptote. Okay, and I think we can confirm everything. We said it was increasing to the left of -2. We said it was increasing from -2 to 0, and then decreasing from 0 to 2, and decreasing from 2 to infinity, right? I think this is it. This is the graph that we get. Let's go paper. I don't know how many, it takes a lot of focus. I don't know how many more of those I can do right now because I'm kind of tired. Let me see. We'll do at least one more. It takes a little while, but it's totally possible. Okay? So just take your time and do the best you can. So let's see. Sketch the graph. So that we found the intercepts, we found our X and Y intercepts or whatever was there. Vertical asymptotes, plus or minus 2. Horizontal asymptote we found. There was no slant. There was no slant since the degree of the numerator is not one more than the degree of the denominator. Derivatives and domain. F prime, we got that. I think we got this for the F double prime, right? We got the same thing. The domain is all reals except plus or minus 2. Okay, so we got that. Critical values, so we should have just called that suggestion critical values. I think we got plus or minus 2. Since F does not exist at plus or minus 2, X equals 0 is the only critical value. We got that same thing. And then they did increasing or decreasing in extrema, right? And so they used the second derivative, right? Okay, so we did all that. Points of inflection, we use a second derivative test, so that there were none, but we can still talk about concavity. Okay, that's fine. So then since there are no points of inflection, the only places where F could change concavity would be on either side of the vertical asymptote. Note that we already know from step E that F is concave down at X equals 0, so we need only a test point from negative infinity to 2. That should be negative infinity to negative 2, and from 2 to infinity. There should be a negative here. Because that's exactly what I had to do right here. It needs to be a negative there. Okay. So then they did a test for concavity by choosing negative 3 and 3 like we did. They got a positive and a positive. So F is concave up from 2 to infinity. And you get this. Same thing we got. And then sketch the graph using information they graphed, right? So we use the information that was given and they just chose a few additional values of X and found the corresponding Y. Okay. Let's try one more. So now, all right, let's go through those. Let's go through those suggestions again. I was gonna jump straight to the graph, but then I was like, no. So the first suggestion, let's see if we can find any intercepts. Okay. And I recommend starting with the y-intercept first. Oftentimes I feel like that was easier. So the y-intercept, we said X is 0, e to the power of 0 is gonna be 1. So when X is 0, the corresponding Y is 1. Okay. So we got a y-intercept. For the x-intercept, we set y equal to 0. For the exponential function, I don't think we can find the x is going to make that 0. Multiplying the inside by a negative like that flips it horizontally, but then we have that x squared, right? But those don't move it up and down at all. So x-intercept, we're going to say none. Okay. So then previously, when we found the x-intercept, then we talked about any asymptotes. So let's talk about any asymptotes. Okay, so since we're dealing with exponential, it should have a horizontal, there should be no vertical asymptote. So for the vertical, I'm gonna say that there's none there. Because we're dealing with exponential. But then for exponentials generally have a horizontal. So let's see. Now, as x goes to positive infinity, we're going to get e to the negative infinity, right? Let me think about that. So that tends to 0, right? So for the horizontal, So I'm just gonna write it like this. As x goes to, first I just did positive infinity. I'm gonna say f went to 0. As x goes to negative infinity, this function goes to infinity, right? So we have a horizontal asymptote is going to be y equals 0. That's as x goes off to the far right. Okay. Let me see. After asymptotes, what else do we do? Vertical asymptotes. Oh, so then we did the derivatives, right? So we use like the first derivative, second derivative. Give myself some space. So next, let's find derivatives in domain. So then the third part were derivatives and domain. Okay. So here, f of x is e to the negative x squared. Okay, let's just take that guy. Let's go ahead and find f prime. Okay, f prime of x. So the derivative of e is itself. So it's going to be e to the negative x squared times the derivative of the exponent. So that's going to be times a negative 2x. Right? I'm just going to rewrite this. So we get negative 2x e to the x, e to the negative x squared. Right? So this is our f prime that we got. So then let's go ahead and find the second derivative. So it's a derivative of the derivative. So we got to use the product rule first times the derivative of the second. So it's going to be this guy times the derivative of the second is just a repeat. So that's 2x e to the negative x squared. So the first times the derivative of the second plus the second, which is this, times the derivative of the first, which is going to be negative 2. Okay. Now we could factor out, I don't know if this helps us, but we could factor out a negative 2. Here, let's do it like this. Negative 2. They both have at least one negative 2 and an e to the negative x squared, right? Here. Negative 2, e to the negative x squared, e to the negative x squared, negative 2. I'm just going to factor that out. Let's go style. Hopefully that helps us. So this is going to be equal to, and I'll write it like this, negative 2 e to the negative x squared, okay? So now in that first part, we're left with negative 2x, okay? The blues we've already accounted for, and I think we accounted for those blues as well. So then I think we're going to say plus 1. So then if we were to multiply back really quickly, this times this, I think that's I feel good about that. And then this guy times 1 gives us this. Okay. So this is the second derivative that we get. The domain of the original, generally speaking, the domain of E is all reals. If we focus on the exponent, that domain is all reals as well. So there are no restrictions. So we're going to say the domain of f of x should be negative infinity to infinity. There are no restrictions anywhere, right? Every x is accounted for. Okay, we're almost there. Just hold on. All right, so we did derivatives in domain. Next, we want to see any critical values. So number 4, any critical values. That comes from the first derivative. So critical values are going to occur when the first derivative is either 0 or undefined. I think x x equals 0 makes that 0. Since we got that negative exponent, I don't think that we can't make the denominator 0, but x equals 0, right? So critical value is going to be x equals 0. So then we'll do extrema. I guess we can go ahead and do the extrema. So then we need to do a test for extrema and increasing, decreasing. So then we're doing extrema and increasing and decreasing, okay? So there's only one candidate, all right? So if we draw a number line, and we're considering x equal to 0, we want to evaluate this in the first derivative on the left and right side of this critical value. So for instance, if we plug in -1 into our first derivative, if we plug in -1, -1 squared is +1. Again, this is order of operation, this guy here. You got to decide which do you do first, multiplication or exponents, and I don't think the original had parentheses, right? So you have to decide which do you do first, multiplication or exponents? It's going to be exponents because in order of operation, we do exponents before multiplication. So with that, when x is -1, -1 squared is +1 times this negative makes it -1. E to the -1 is still positive, and then negative times a negative, ultimately that's going to be positive, right? So everything here is positive, so that means the original function is increasing. Let's check on the right-hand side of 0. Okay. So if we test +1 in the first derivative, we'll get e to the -1. So this is going to be positive times a negative is ultimately going to be negative. So we got that this is negative, which means our original function is decreasing on this interval. Okay. So then that means that we have what, a relative max? When x is 0 and the original is 1, right? Relative max at 0, 1. We're almost there. Just hang on. So then, now that was analyzed in the first derivative. Now the second derivative tells us about points of concavity. So we'll say points of inflection / concavity. Did they do those in separate? Let me go back and see something really quickly. Concavity, right? And then inflection points. Okay, so let's do inflection points first. Points of inflection. So that's where the second derivative is either 0 or undefined. Second derivative is here. So in order for this to be 0, if we set the second derivative to 0, we can use the 0 factor property. Let's see, if we focus on this guy, I don't think this will ever be 0. All right. Okay. But this one can be 0. If we set this equal to 0, subtract, divide, I think we get a half. So a candidate is going to be x equals 1/2. So then let's look at, but we need to look at our concavity to confirm whether this is a point of inflection or not. So then let's look at concavity. Okay, concavity. So we take this candidate for the point of inflection, which was x equals 1/2. And we need to evaluate, choose points on the left and right side of this and evaluate it in the second derivative. So for instance, if we plug 0 into the second derivative, let me see, e to the 0 is 1. So this term is negative. Okay. And then this is positive. A negative times a positive is negative, right? So on the left-hand side of 1/2, we got that the concavity was negative. So that means our original graph is concave down. To the right of 1/2, if we choose 1 in the second derivative, right? E to the negative anything, still going to be positive. So then that means this term is negative. If we plug in 1, this is negative. So double negative is positive. So then over here is positive. So that means we're concave up. So then we have a point of inflection when x is 1/2. The corresponding y from the original, oh shoot, did I go back too far? No. I feel like I made some mistakes. Let me see, when x is 1/2, e to the negative 1/4, whatever that number is, e to the power of a negative 1/4. Let me crunch that number really quickly. So then if I do e to the power of a negative 1/4, okay, so I'm gonna say it's like approximately like, we can do just 0.78. It's approximately 0.78, okay? So we do have a point of inflection, provided we haven't made any mistakes. We got our intervals of concavity. So then if we put all this together, now we're gonna sketch the curve. Okay. And then actually, let me just pull a copy. This, I'm gonna copy, paste it right there. Okay. So now, let's see. Let's put all this together. So we got a y-intercept of 0, 1, okay? 0, 1, so we got this. There was no x-intercept. We said there was no vertical, but we had a horizontal. X went out to the far right. So we do have a horizontal asymptote, y equals 0, okay? So we're just gonna capture that like this. Okay. And that's y equals 0. Okay. So we got our y-intercept, we got a horizontal asymptote. The domain is all reals. So we said we had a relative max. Let me think about this. How could this go? Let me check this one more time. So if we take -1 and plug it into the first derivative, right? If we plug in -1, this is positive. This is positive. Yeah, positive, right? So then now if we take 1 and plug it into the first derivative, this is negative. This is positive. Okay. Well, let's just keep going. So we had a max, so that's a relative max. Let me think about it. It could be like this. I'm trying to get a sense. Okay, so we got a relative max. We said we have a point of concavity at 1/2 comma point. So it's a point of inflection. So let's capture that. So 1/2 and then 0.78. So 1/2 0.78 is about here. Okay, I'm just gonna go like this. Let's see. We know it gets close. And we said that that's a max. Oh, okay, I see it. We know we finished close going off to the right. It passes through, oh, you know what? No. Let's keep going. So it needs to be concave up. Somehow this is concave down. I'm gonna choose a few additional points to the left, right? So for instance, when X is -1 in the original, let me get a copy of this. So we'll just choose a few additional points. I probably should write it out in the table, but when X is -1, we get e to the -1. That's 0.3. So maybe there might be another horizontal. As X goes to -infinity, oh, it goes to 0, right? Okay, so we do have a horizontal. I don't know why I didn't check going to the left, right? Right here. For the horizontal, as X goes to positive infinity, Y tends to 0. I don't know why I keep neglecting it. I mean, we still captured it as X goes to -infinity. F tends to 0 as well, right? So when you go in either direction, it tends, it's still Y equals 0, right? And I don't know why I was like hesitant about that. I want to say this might be symmetrical. So then, okay, I think we're ready. So then we'll get basically a graph like the following. It's going to start close to this asymptote, you know, pass through some points here. Here, we can do a test for symmetry. If we evaluate f of -x, the whole thing. But I'm just gonna, I think that point is there. And we can check and test to make sure that it's working. I'm just trying to get past this. So then we start close to the asymptote, we pass through these points, and then we finish close. I think that might be the graph. All right, and then to be sure, we would just, oh, wait a minute. Concavity. I think we're missing something. Points of inflection. Because we should have, it might be 2 of them. I think we're missing something. Okay, point of inflection. That's where the second derivative is going to be 0. We got one of them. What about this guy over here on the right? If it's 0, you divide e to the -x. It won't be 0. I feel like I'm missing something somewhere. Oh, I think I found it. Right here. I knew it was something. Something was off. I found it. Okay, right here. We factored out this -2 and this blue guy. We captured one of the x's, and I think we missed the other x. So this was really supposed to be -2x squared for the second derivative, right? So then if we set that to 0 and solve, we'll have 2x squared equals 1. Okay, let me write that one out for the point of inflection. So we get 2x squared equals 1. I'm just coming back. 2x squared equals 1, divide x squared equals a half. Take the square root. So then x equals plus or minus root 2 over 2, right? So it's 2, yeah, because when I was graphing, we had missed that red part right there. So then the point of inflection, we had 2 of them that we should have been testing. So we missed one because we missed that square. So we need to back up a little bit right here. So let me strike through this. I'm going to leave the arrow there. Let's get rid of this stuff. Right here, we need to get rid of this thing, this, and this. Okay. Okay, so we had 2 points, because when I was graphing, I was like, these are 2 points of inflection. And it's not the half. It's going to be this plus or minus root 2 over 2. And root 2 over 2 is like 0.7 something. So which is close to a half. That's why I was like, it was close, but it wasn't all the way there. But again, because what we had before was the wrong thing. So if we take this, here's negative root 2 over 2 and positive root 2 over 2. Okay. So if that's like 0.7, I think that's 0.7. Hey Siri, what's the square root of 2 divided by 2? Hey Siri, what's the square root of 1/2? 707, right? So approximately 0.7. So if that's a negative 0.7, to the left would be something like -1. If we plug in -1 into the second derivative, right here, if we plug in -1, this is positive. So this whole thing here is negative for this term. I think this is negative as well. So then we get double negative. So then this is going to be positive in this region, which means our original is concave up, which is correct. Okay. Well, based on the graph that we have. If we choose a number between negative root 2 over 2 and positive root 2 over 2, we choose 0. If we plug in 0, this term is negative, all right? And this is positive. So negative times a positive is negative. So then we have a negative in here and it's concave down. And then to the right, if we choose 1, same kind of thing, right? This is positive, so that means this term is negative. 2 plus 1 is negative, double negative is positive. So what that means is that over here, it's concave up, okay? So that means we have 2 points of inflection, these x's with the corresponding y. All right, we should plug it in to get the proper thing. We said that this was a relative max, right? I think this is okay. And we should just, these numbers, it really should be root 2 over 2, and then we need to plug that into the original. If that's a square root of a half, that's a square root of 1/2. When you square, you get a half, so e to the half. So then, to be more precise, this is root 2 over 2. And then this is going to be e to the power of a negative 1/2. And then the point over here is going to be negative root 2 over 2. And it's going to be, I think, the same thing, e to the negative 1/2. Okay, that was an adventure. But we get a graph like this. Okay. So now let's look at the prepared notes and see how do we do. And again, some was off because I was like, it wasn't adding up. We had to go back and clean some stuff up. That happens, right? All right. It's taking way longer than I would have liked, but that's okay. So intercepts is, since this is equal to 1, the y-intercept occurs there. There are no x-intercepts, okay? Asymptotes, so the line y equals 0. Again, as x goes to positive infinity, this function tends to 0 in either direction. As x goes to positive infinity or negative infinity. F prime, we got this. F double prime, okay, they left it there, that's fine. And then the domains of everything was all reals. So x equals 0 is a critical value, or, oh shoot, did we get that y-intercept? Y equals 1. Yeah, okay, let's keep going. Okay, on the y-intercept. The critical value x indicates 2 intervals. So we have a relative max occurs at 0. So it's increasing to the left of that and decreasing on the right. That's fine. Inflection point. See, and we have forgot the square. So then we found it. We went back. We did our plus or minus √2 e to the negative 1/2. So we got all that. We fixed it. Concavity. Then you do your test intervals. So I think it went from concave up, concave down, concave up. So we had 2 inflection points. Right. So we captured both of those. And this was the graph that we got. Look at God. That is a real adventure, right? That was an adventure. I am spent. All right, I'm good. I'm going to stop until class time. So once class starts, I'm probably just going to play this for you guys and be working on the next section. Okay. I'm going to leave this summary for you. I'm done. Okay, we can do it real quick. So a line x equals a is a vertical asymptote if the limit as x approaches a from the left tends to plus or minus infinity, or the limit as x approaches a from the right tends to plus or minus infinity. A line y equals b is a horizontal asymptote if as x goes to infinity, y goes to some number, or as x goes to negative infinity, y goes to a number. A graph may cross the horizontal asymptote, but never a vertical asymptote. A slant asymptote occurs when the degree of the numerator is one greater than the degree of the denominator. Long division of the polynomials can be used to determine the equivalent of slant asymptote. And then vertical, horizontal, and slant asymptotes can be used as guides for accurate curve sketching. Asymptotes are not a part of the graph, but are visual guides only. Okay. So that was an adventure. That one little power of 2 was throwing off our results. I was like, why is this weird? Something's off. It just, things weren't adding up. And then I went back and looked at it. I was like, oh, I found the mistake, right? So with that, the adventure is over. We're going to end the session here. Let me go ahead and make a copy of this available for you guys. I'm going to share. I want to send it to Box, not College Algebra. This one, Calculus for Business, Notes, Handwritten Notes. We just did the read 3, so we're going to drop a copy there. All right. And once that bar finishes loading, you'll have a copy. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. Peace.